OSPF routers cycle through 7 distinct states to establish and maintain neighbor adjacencies. The process begins in the down state, transitioning to the init state upon receiving the first hello packet. After two-way communication is confirmed, they enter the two-way state, where the DR-BDR election occurs on multi-access networks. The routers then enter the XStart state and exchange state to negotiate the master-slave relationship and share summarized database information via DBDs. In the loading state, missing link state information is requested and sent, LSRS/LSUS, culminating in the full state, where the link state databases are synchronized and routing can fully commence. When OSPF-enabled routers are first connected, they transition through specific operational states to establish a relationship. In the down state, no hello packets have been received, although the router may still attempt to send them to discover neighbors. Once a router receives a hello packet containing its own router ID in the neighbor list, it transitions through the init state. The process culminates in the two-way state, which signifies that bidirectional communication has been successfully established between the two devices. On multi-access networks, such as Ethernet, this state is also where routers decide which ones will take on the roles of designated router DR and backup designated router BDR. These initial stages are critical because they form the foundation for exchanging further topology information. After establishing bidirectional communication, routers enter the XStart state to decide which router will initiate the exchange of database information. During the exchange state, routers trade database description (DBD) packets to compare their local link state information with their neighbor's data. If discrepancies are found, the routers transition to the loading state, where they use link state requests (LSRS) and link state updates (LSUS) to retrieve missing records. Once all routers have synchronized their databases and possess an identical map of the area, they reach the full state. This final state signifies that the adjacency is complete and the routers are fully operational for routing traffic. Together, these steps ensure that every device in the OSPF network maintains a consistent and accurate view of the topology. To establish neighbor adjacencies, an OSPF-enabled router sends hello packets out of all active interfaces using the reserved multicast address 224.0.0.5. These packets contain the router ID, a unique 32-bit number formatted like an IPv4 address that identifies the router within the OSPF area. When a neighboring router receives this hello packet and does not recognize the sender's router ID, it begins the process of establishing a formal adjacency. This discovery mechanism is essential for OSPF v2 routers to automatically find each other on a network segment without manual configuration of every peer. Once the routers recognize each other, they can transition through the operational states to synchronize their databases. By using a standardized multicast address, OSPF ensures that only other OSPF-capable devices process these discovery messages. Establishing an OSPF adjacency begins in the down state, where routers send hello packets to the multicast address 224.0.0.5 to discover peers. Upon receiving a hello packet that lists its own router ID, a router moves from the init state to the two-way state, signaling that bidirectional communication is successful. In multi-access networks like Ethernet, the two-way state is also where routers elect a designated router, DR, and a backup designated router, BDR, to manage link state updates efficiently. Following this, routers enter the XStart and exchange states to decide which router starts the synchronization and to trade summaries of their link state databases. If a router needs more detailed information, it enters the loading state to request specific link updates until its database is current. Finally, once all databases are perfectly synchronized, the routers reach the full state, indicating a fully established neighbor adjacency ready for routing. After the two-way state, routers begin a three-step database synchronization process starting with the XStart state, where the router with the highest router ID is selected to initiate the exchange. During the exchange state, routers trade database description (DBD) packets, which must be formally acknowledged by the receiving peer using LSACK packets. If a router discovers it is missing information or has outdated records, it enters the loading state to request specific details using link state requests (LSRS). Once all requests are satisfied and the databases are identical, the routers transition to the full state, signifying complete synchronization. To maintain this accuracy, OSPF sends incremental updates via link state updates LSUS whenever a network change is detected. Additionally, OSPF performs a parachute refresh by resending link state information every 30 minutes to ensure the topology remains consistent over time. Multi-access networks, such as Ethernet, present two significant challenges for OSPF: the creation of an excessive number of adjacencies and the overwhelming flooding of link state advertisements, LSAs. If every router on a common link established a formal adjacency with every other router, the number of connections would grow exponentially, consuming unnecessary bandwidth and resources. Furthermore, because routers flood LSAS whenever OSPF is initialized or a topology change occurs, a high-density network would be inundated with redundant update traffic. To manage this, OSPF requires a mechanism to streamline how routers communicate on these shared segments. By limiting the number of full adjacencies, the protocol can significantly reduce the volume of control traffic exchanged between peers. This optimization is essential for maintaining network performance and ensuring that OSPF can scale effectively in large-scale Ethernet environments. In multi-access networks, an increasing number of routers leads to an exponential rise in link state advertisements, LSAs, which can cause chaotic network traffic if left unmanaged. To solve this, OSPF elects a designated router DR to act as the central collection and distribution point for all LSAS on that segment. A backup designated router, BDR, is also elected to immediately take over these responsibilities should the DR fail. All other routers on the segment are classified as drothers, meaning they only form full adjacencies with the DR and BDR rather than with every other router. This structure significantly reduces the volume of redundant flooding by ensuring updates are sent once to the DR and then redistributed. It is important to note that the DR role only applies to LSA dissemination. Standard data packets are still forwarded using the best next hop router identified in the routing table.